Hello everyone, this is Lecture 14 of ComSci 141, Turing Machines. Previously, we discussed the second part of ComSci 141, which is about context-free languages and pushdown automata. We talked about context-free grammars, parse trees, pushdown automata, the equivalence of PDA and CFG, and the properties of context-free languages. Now, we will move on to the third and last part of ComSci 141, which is all about Turing machines and recursively enumerable languages. In today's video, we will discuss Turing machines. We will learn of its 7-tuple notation, how to write instantaneous descriptions, how to design Turing machines, how to distinguish between Turing machines by final state and Turing machines by halting, the recognizer versus decider Turing machines, and the equivalent language, which is recursively enumerable languages and recursive languages. We will also discuss the Chomsky hierarchy of languages. Okay, so let's start. So far, we have seen several computation models in this course. So first, we saw finite automata, which models regular expressions. We also saw pushdown automata, which modeled parsers. Now this time, the third computational model that we'll encounter is the Turing machine, which models a computer. So what is a Turing machine? Well, it's not this one. Well, get it? Turing machine. It's not this one. But a Turing machine actually looks like this. Okay, so if you look at this drawing, there's a infinite tape here wherein you could read and write symbols. Okay, and then there's a tape head right here which points to a certain cell, um, and then there's also a state. Okay, so we'll talk more about that in a while. But so far, in the theoretical machines that we have seen, so we've seen finite automata, which was about states and transitions, and it had very limited memory because it only remembered the current state, right? So it only remembered one thing. The pushdown automata was a slight upgrade in terms of memory because you can think of a PDA as an epsilon NFA with a stack. Okay, so it now has memory, but it's still restricted. Why? Because you can only see and change the top of the stack. Okay, so even if you have some type of memory, you're only allowed to change the top of the stack and see the top of the stack. Okay, so it's also restricted. Now, Turing machines, on the other hand, is like a DFA with unlimited and unrestricted memory. Okay, so unlimited, that means that it has an infinite tape, and unrestricted, that means that you can read and write on any of the cells on the tape. Okay, so a Turing machine is an abstract computational model, and by abstract, it means that it's purely theoretical. It's not for practical use. Okay, but it is more powerful than your finite automata and PDA. Well, due largely to the part uh, to this part, okay, that it has an unlimited and unrestricted memory. Okay, and in general, it models a general purpose computer. Okay, so whatever a computer can do, theoretically, a Turing machine can also do it. So Turing machines are named after Alan Turing, its inventor. Okay, and when he created it, he intended it as a hypothetical computer, not for practical use. Because in reality, he created Turing machines even before computers were created, right? So it was in 1936. It was computers were not yet, or like physical computers were not yet made by then. Okay, so it's not for practical use, but the goal of Alan Turing when he created Turing machines was to understand the limits of computation. Okay, what can a computing machine do and not do? Okay, so we will learn more about limits of computation in later lectures. Okay, when we talk about undecidability and intractability. But yeah, that was the reason as to why Alan Turing created this machine. Now, let's talk about the power of the Turing machine. So In terms of computation power, it is as powerful as any general purpose computer, as I mentioned earlier. In fact, it's even more powerful because a Turing machine has infinite memory, whereas our computer has a finite memory, right? So when you buy a computer, you're supposed to ask how much memory does this computer have, like one terabyte or 2 terabytes or 500 gigabytes and so on. So it has finite memory, but our Turing machine, since it's only a theoretical machine, it can have an infinite amount of memory, okay, unlimited amount. So in fact, it's more powerful. Okay, so even if it's very powerful because it has a lot of memory or unlimited memory, it still cannot solve all problems. Okay, because as we'll learn later on, there are some problems that are beyond the theoretical limits of computation. So there's just certain problems that a computer cannot solve. Okay, so yeah, we'll learn more about that in about 2 lectures from now. Okay, so let's talk more about the parts of the Turing machine. So what are the parts of the Turing machine? So first we have, of course, the states, the current, starting with the current state. So it will remember what the current state is. Okay, and then for the memory, it will have the infinite tape shown here. So this is the infinite tape. Okay, and then the tape head is the pointer, which tells you where in the infinite tape you're currently looking at. Okay, and then for the standard Turing machine, the tape is infinite to the right, just like this. Okay, so it starts here and then extends all the way to the right. But in other cases, the tape is infinite in both ways. Okay, so there are some versions of Turing machines that have an infinite tape both ways. Okay, but for the standard version, it's infinite to the right. Okay, now for the actions, so what can a Turing machine do? So on the tape, you can read from the tape. Okay, you can read symbols that are written on the tape. You can write on the tape, so you can overwrite what is currently written, or if it's blank, then you can add symbols onto the tape. So this is already more powerful than the PDA because in the pushdown automata, you can only push and pop from the stack, no override. Okay, and you can only even change the top of the stack, right? You can't write or read or write anywhere else, but just only on on the top. Okay, whereas here in Turing machine, you can read and write anywhere on the tape. Okay, next the tape head. So what does the tape head do? The tape head will move to the left or move to the right. Okay, so you allow movement of the tape head so that it can change or point to a different cell to look at. So this behavior allows you to overwrite any cell in the tape because you can move the tape head so you can reach any cell in the tape theoretically, right? Whereas, as I mentioned, the PDA can only change the top of the stack. For the state, well, you can change states. Okay, you can transition from one state to another. And the curious thing about Turing machines is that accepting states take effect immediately. Okay, what does this mean? In the DFA, you only reject or accept the input string if you have finished processing the input string itself, right? But um, in the Turing machine, even if you haven't processed the whole input string, but once you reach a final state, then it will take effect immediately. You're already accepted. Okay? So once you go to a final state, even if you haven't finished processing the whole string, you're done. Okay? That is not like in DFA, because in DFA, even if you pass through a final state, but if it's not yet the end of the input, you might end up in a different state altogether, right? So you only decide at the end of the input string, okay, in DFA. But in Turing machines, that's not the case. Okay, so accepting states take effect immediately. Okay, so that's the behavior of Turing machine. So let's now look at its 7-tuple notation. So what are the 7 things that make up the Turing machine? So first is sigma, which is the input alphabet. Q is the finite set of states. Delta is the transition function. Q sub 0 is the start state. F is the set of final states. Gamma is the tape alphabet. Okay, so the input symbols that are written on the tape. And dollar is the blank symbol. So what represents blank in on the tape? Okay, so we're familiar with most of this, if not all, right? So sigma, we've seen this a lot of times in PDA and in DFA. Also the set of states, transition function, Q sub 0 and F. And then for gamma, in PDA, this was the um, stack alphabet, right? But in this case, this is the tape alphabet. And then instead of a Z sub 0, which is the bottom marker of the stack, we have the dollar, which is the blank symbol on the tape. Okay, so more or less everything is the same except for the transition function. Okay, so it's the transition function that we will focus on. Okay, so the transition function of a Turing machine looks like this. Okay, so you have delta qz is equal to p, y, and then a direction. Okay, so let's break each part down. So q is the current state. So you're in current state q, and then z is the current tape head symbol. So the tape head is pointing at this symbol currently. Okay. And then P is a state that you transition to, and then Y is the tape symbol that you replace Z with. Okay, so Z becomes Y, and then D is the direction. So after um, changing from state Q to P and changing the tape symbol from Z to Y, you move the tape head either left or right, one cell to the left or one cell to the right. Okay, so all in all, for the state, you change from Q to P, as I mentioned. And then on the tape, you replace Z by Y. And then the tape head will move one cell in the direction of D. So it's either left or right. Okay? So those are the three things that you can do in one transition. You can change the state, you can replace the tape symbol, and then you can move the tape head. Okay? So now, how does the Turing machine actually do its computation? So first, you put the input string on the tape. Okay, so the tape has an infinite number of cells. So you put in the input string on the tape, one symbol per cell. Okay, then the rest of the tape contains blank symbols. Okay, this is where the dollar sign comes in. So the dollar sign is the blank symbol. The first dollar sign marks the end of the input. Okay, so you start the tape head on the leftmost cell of the tape, say at the at the start. Okay, and then the Turing machine will move according to the transition function. So just follow the transition function. You change the state, you change the tape symbol, you move the tape head, and so on. Now, if the tape head is at the leftmost or at the start cell of the tape, and the transition function tells it to go left, so there's nowhere to go, right? It will just stay at the start cell. Start cell. Okay, it will not move because it's already the leftmost. And if you tell it to go left, well, there's nowhere to go. Okay, and this is in the standard Turing machine, wherein it's only infinite uh, to the right. Okay, but if it's infinite both ways, then of course you can go to the left if you want to. Okay. Now, how does it stop? The Turing machine stops if it enters a final state or when it has no moves left. So as we'll learn later on, there are two types of Turing machines. There's a Turing machine by final state and there's a Turing machine by halting. So you either stop if you reach a final state or you stop if you have no moves left. Okay. So take note, however, that a Turing machine could go on forever, never halting, because uh, the movement of the tape head could get stuck on an infinite loop. Okay, so it could get stuck, so it could go on forever, never stopping. Okay, and since it's theoretical, it's not bound by the laws of physics, or wherein you need electricity for the computer to function and so on. There's no such thing because it's a theoretical computer, so it could go on forever. Okay, so that's how the Turing machine does its computation. Okay, next let us look at the instantaneous descriptions. So you've already seen this notation before in PDA, right? So it describes a snapshot of the current state of the Turing machine. So it's a convenient way to write how does the Turing machine look like currently. Okay, so this is useful in showing TM computation, especially if you're writing it on a paper. So in the PDA, the instantaneous description had three parts. You have the state, the string, and the stack contents, right? In the Turing machine instantaneous descriptions or Turing machine IDs, it will look like this: A, Q, B. Okay, so what are this? What are these three things? Q is the current state, okay, and A and B are tape contents. Now, where Q is located indicates where it is currently pointing. So the tape head is currently pointing at the first symbol of B. Okay, so let's see some examples. If it's like this, Q000, that means that, okay, if it's this one, so Q is the current state, right? And it's currently pointing at this one, 000, right? So it's pointing at 0. Next, how about if it's 1Q00? So Q is pointing at this 0. So that would be 100. So Q is pointing at this one. Okay? So this is the infinite tape. Dot, dot, dot. Same thing here. Okay? So the current state is Q and the current tape head is pointing at 0. Finally, how about if you have 111Q? Well, if that's the case, then you have 1, 1, 1, and then Q is right here. So if this is the infinite tape, you have this. And this is supposed to be a dollar sign. It's a blank, right? So Q is now pointing at the end of the string. Okay, so this is how the instantaneous descriptions are uh, this is how they look like in actual Turing machines. Okay, so yeah, hopefully that's clear. Okay, it also follows the goes to relation. We have the turnstile symbol. So ID1 goes to ID2 in one move, and then goes to star if it's in 0 or more moves. Okay, so it's similar to the goes to relation in PDA. Okay. Okay, so let's now see some examples of Turing machines. So we will look at 5 different examples so that you'll be familiarized with how to design Turing machines. So we will look at how to create Turing machines for a regular language. This is A plus B star, quantity star. So any string consisting of A's and B's. You have an odd binary checker. So given a binary number, is it odd or even? Or yeah, is it odd basically? Then you have A and BN. This one is a context-free language, right? So um, bunch of A's followed by a bunch of B's, and there should be an equal number of A's and B's. Okay, this one WCW, wherein the W here is any combination of A's and B's, and then there's a C at the middle, and then whatever is the combination of A's and B's here should be the same combination here. Well, this one is not context free anymore. Okay, so we'll learn how to design a Turing machine for this one, and then finally, um, we'll also do something like a binary number plus one. So you add 1 to the current binary number that is given as an input. Okay, so we'll look at those 5 examples. So let's start with first one, A plus B quantity star. So this is a regular language, as I mentioned, because of the regular expression, and you only accept if all symbols in the input string are either A or B. Okay, so as long as it's A or B that you are seeing, you should be fine. So the Turing machine for this is pretty simple. You only have two states. You have Q, which is the starting state, and F as the final state. Okay, so Q, each time it sees an A or a B, it will keep it as is, so it will not change it, right? Still in state Q, still A, still in state Q, still B, and then you just go to the right. Okay, so if you see an A or B, just pass through it because those are fine, those are accepted. Okay, and then you only transition to the final state if you reach the end of the string, the dollar sign, the blank symbol. Okay, so if you see the blank symbol, that means that everything that you've passed through so far are A's and B's. So you will go to the final state. And as we mentioned, once you reach the final state, it's already accepted. Okay, so yeah, it's as simple as this. So let's see AABA. Okay, so starting at state Q, it will see an A, so just pass through it. It will see another A, so it will pass through it. It will see a B, so pass through it. It will see an A, so it will pass through it. And then it's now at the end of the string, so it will now transition to state F. Okay, so it's now accepted. How about this one? BBCA. Q sees a B, okay, pass through it, sees another B, pass through it. Now it sees a C, and it doesn't know what to do when it sees a C, right? So it will stop. And since you are in state Q, you're not in a final state, then it is rejected. And that is because we don't accept anything that is not A or B. Okay? So yeah. So let me show you an an illustration, a demo of how it looks like. So how about A, B, A, B, B? So it will just be simple. It will just pass through it, B, B, and then at the end of the string, it will stop, and it's accepted because it's now in state F. Okay? If we have all A's only, A, 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 that's also accepted. Even if it's all B's, it should be accepted as well, right? But if we add A, B, A, B, and then we add a C somewhere here, okay, let's load that. Now it's when it encountered the C, it's rejected because it's not defined what to do when we encounter a C, right? So it will stop because it doesn't know what to do. Okay, so that is A plus B quantity star. So it's pretty simple, right? Okay, next example, check if a binary number is odd. Okay, so you're given a binary number, is it odd or even? Now, to check if a binary number is odd, it's actually pretty simple. Just check if the last symbol is 1, right? Because if the last symbol is 1, then that is odd. If it's 0, it's even. So it's actually the regular language, 0 plus 1 quantity star, and then 1 at the end. Okay, so look, what we'll do is we'll look for the end of the input string. Okay, so we'll just pass through the zeros and ones. We'll ignore it. Look for the end of the input string, and once you reach the end of the input string, you go back to the left. Okay, go to the left and check the last symbol, and then that's when you decide. If it's 1, then you accept it. If it's not, then you reject it. Okay, so simple as that. So this is the transition function. So at state Q, so we have how many states? 4 states. Q is when we look for the end of the string. So if it's zeros and ones, we'll just ignore it, right? We'll just go to the right. Okay, go to the right until we reach the end of the string, which is dollar. Okay, so once it sees the dollar sign, the blank symbol, you go to state D, okay, and you go to the left. You go back to the left, so you go back to the last symbol. And then in state D, If you see a 0, then it's even, so you reject it. Okay, you go to state R, reject. Okay, but if it's 1, you go to the final state since it is odd. Okay, so simple as that. So if you have 0, 1, 1, then from state Q, it will just pass through everything. No, so 0, 1, 1, it will ignore that. And then now we've reached the end of the string. So we will go back to the left and go to state D and decide. Okay. In state D, check the current symbol. It's 1. So it is odd. So we'll go to state F. It's accepted. And then what if it's even? So same thing for state Q. Just go to the end of the string and then go back to the left and go to state D. And now in state D, you see a 0. So you reject. And then that's when we stop. Okay. And it's not the final state. So this is not accepted. Okay, so let's see that in action. So for this one, it will just pass through everything, look for the end of the string, go back to the left, and then it says a 1, so it's accepted. Okay, now how about if it ends with a 0? Same thing, so it just pass through everything, look for the end, go back to the left, sees a 0, so it rejects. Okay, because this is even. Okay, so simple as that. Okay, next. ANBN. Okay, this is a context-free language, right? So number of A's, certain number of A's followed by a certain number of B, wherein the number of A's and B's should be equal, and N should be greater than equal to 1. So what we'll do for this Turing machine is, well, we know that the first thing that we'll encounter would be A's, right? So if we see an A, what we'll do is we'll go to the right to find the B that it is supposed to match. So all of the A's here has to match all of the B's here. Okay, so once you see an A, look for a B that is supposed to be its pair, and then you mark both of them. Once you mark both of them, they're already processed, and then you repeat the whole thing until everything is marked. Okay, so after finding the pair, go back to process the next A, and this process will repeat. Okay, so we have several states for this one. So we have state QA. This state is looking for A. Uh, you're supposed to find A and you mark it as X. Okay, that means that you have finished processing this A. And then you have state QB, which is finding B, and once you find it, you mark it as Y. Okay, so we'll have different markers for X and Y so that it won't be confusing. Because if it's X and X, then we might not know where the start and end of the A-B division would be. Because maybe if we mix them, if it's all X's, then the Turing machine might get confused. So it's better to mark them in different, using different markers. So A would be marked as X, B would be marked as Y. Okay, and then the state QX is just going back, going to the left to look for the last X marker that it encountered. Okay, and then QE is the state we're looking for the end of the string. So this is going to the right to look for the end of the string. Okay, so um, this state naming of the state is actually pretty helpful. So um, you're conveying your intent, or what the state is supposed to do from the state names itself. So QA is you're looking for state A, for the symbol A. QB is you're looking for symbol B. QX is you're looking for X, and QE is you're looking for the end of the string. Okay, so it's more intuitive with the state names. Okay, and then of course QF is just the final state. Okay, so we'll transition to this if everything is good. Okay, so what will we do for this Turing machine? Okay, so there's quite a lot, so let's try to unpack it one by one. So you start at QA. Okay, since you know that the first thing that you're looking for is A's, right? So let's have a running example here. Let's say A, 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 B, B, B. So this one will be accepted, right? So it's supposed to be A N B N. So if you're at QA, and you see an A, you change this A to X. So that means that this is processed. So this will be replaced with X. Okay? And then change to state QB to find the match. Okay, so you won't be at QA anymore. You will go to state QB. So you go to the right to look for B. So you're now at QB to look for B. Now, if you're at QB and you see an A, you just ignore these A's because that's not what you're looking for. You're looking for a B, right? Okay. And if you see some Y's along the way, you also ignore that because those were processed B's and you don't really care about that for now. Okay. What you're looking for is this B, the um, the terminal B. So in this case, it will find that here. Okay. So once you find B, you change this to Y. So this becomes Y, and change back to state QX. Okay. And go back to the left. So you're going back to the left na naman and looking for the last X that you encountered. Okay. And while in state QX, if you see a Y or an A along the way, just ignore them. Just pass by them. That's not what you're looking for. You're looking for an X. Okay. Once you see the X, then you go back to state QA. Okay, so you're back at QA again, and then you repeat the process. Okay. So that's it. And then when will this stop? Okay, so this will be eventually replaced by an X. So look for a B, replace this by a Y, go back, look for an X, then here, this will be replaced by a Y, and so on. Now, once you're in QA, and then you see a Y, then that means that all A's have already been processed. So you go to QE, wherein you're supposed to look for the end of the string. Okay, so go to the end of the string. Once you see the blank, then you transition to the final state QF. Okay, so if it doesn't if it's not too clear from that explanation, let me show you an example. Okay, but all in all, if you put all of this together, it will be this transition function. Okay, so for QA, you're only interested in looking at the symbol A. So you go to QB, state QB to find the pair B, and then you mark A with X. Okay, and then at QB, if it sees an A, then just go to the right, ignore it, because what you're looking for is the B. Same with Y's. If you see a Y, just ignore it, just go to the right. But once you see the B, you go to QX, mark B with Y, and go back to the left. So for QX now, you're supposed to look for the last X that you marked. Okay, so if you see an A or a Y, just ignore it. Okay, but once you see the X, you go back to QA, so it's back here, and then go back to the right ang direction. So this will loop and loop and loop until at one point QA will see a Y. That means that all of the A's have been processed because A's should be marked by X, right? And B should be marked by Y. So once it sees a Y, that means that you have reached the B part of the string. So transition to state QE. So you're supposed to look for the end of the string, and if you see Y's along the way, just ignore them because you're supposed to look to see Y's along the way. And once you see the end, then that's when you transition to QF. Okay, so let me show you an example. Starting with this one. Okay, so let's go through this slowly. So you're in state QA, you see an A, so you mark this with an X, okay, and then you move to the right and um, change to state QB. Okay, in QB you don't care about A's and Y's, but you're looking for B. So if you see an A, just ignore them and just move past it. Now you see the B, which is what QB is looking for. So this B will be marked by Y, and we will transition back to state QX. So you're supposed to look for the last X that you marked, so that you can move on to the next part. Okay, so go back to the left, and then once you see the X, then you go back to QA and go back to the right. Okay, so this will repeat. So this will be X, and then B, and then Y again, and then look for X, and then you're supposed to look for A, but you see a Y, so that means that everything has been processed. Okay, so now um, you're supposed to look for the end of the string, and since it's the end of the string, then you accept it. Okay, so let's do this again, this time with a longer string, and I'll just play it faster. So X, marked it with Y, and then that A will be marked by X. We paired with this B, marked by Y. Go back to find the X. See that A again, marked by X. See that B, marked by Y. And then everything is paired off. So you look for the end, and then you accept. Okay, so that's it. It's simple, right? Now, what would happen if there were more A's than the number of B's? Okay, so let's try that. If there were more A's, the number of B's. So we have 3 A's here and only 2 B's. What will happen? Okay, so this first two A's and B's would be paired off, right? Okay, so, okay. Now, you're in QA and you see an A, so you mark this with an X. So you're supposed to find its pair B, right? But now, you see the end of the string and you don't find the B. So there is no movement for um, blank on QB, right? Because if you go back to this one, blank on QB is undefined, so it will stop. Okay, so it was rejected. Okay, now what about if there were more B's than A's? What would have happened? Okay, so if there were more B's than A's, then okay, let's try this. A, B, B, B. Okay, and let's try to speed it up. Okay, so the first two again will be paired off, right? Okay, now it's supposed to look for the end, and it's only supposed to be finding Y's along the way, meaning all of the B's should have been paired off. But once it encounters this B, which is unmarked, then it will be rejected because QE is not defined for the input symbol B. Okay? Okay. So go back here. QE on B is not defined, right? So once you see a B, then that means that you stop because there is an unmarked B that was not paired off with an A. Because if it was paired, it should have been marked as Y. Okay? But if it remained as B, then it was not paired off. Okay? So it will also stop. Okay? Now how about if it was mixed A's and B's? It doesn't follow A and B N. What would have happened? Well, what would happen? A, B, B, A. Something like that. Or, yeah. Okay, that's 3. So what will happen is, it will encounter this B, and then it will stop. Right? Or A, B, A, B, A. Okay. It will try to pair off. So A, and then what it sees the B there, okay, it's paired off, but then it sees the A here, which is weird because you're supposed to have paired of X, X, and Y, Y here. So it's looking for the end already, but at on the way to the end, it found some unpaired letters or symbols, so it will stop and reject. Okay, that's A and B N. Okay, let's move on to the fourth example, which is now WCW. This is not Woman Crush Wednesdays. Okay. So for WCW, it's the W here is any combination of A's and B's. The C is at the middle, and then whatever was at the first half should also be at the second half here. It should be repeated. So examples of that would be AB, C, AB, or BBB, C, BBB. And then you have BAB, C, BAB, and then A, C, A. So C serves as the middle point, and then whatever was at the first half should also be the second half. Okay. Now this language is neither context free nor regular. So this already shows that Turing machine is more powerful because this is not context free and not regular, but there is a Turing machine for it, right? So, okay, so there's quite a lot here. So let's try to process this. Okay, let's try A B C A B. Let's try this with green. Okay, what if it's A B C A B? Okay, so you're starting at state Q0, and when you see an A or a B, you mark it as X, meaning it's already processed. Okay, so if you see an A, you mark it as X. So remove this, mark it as X, and then you change to state QCA or QCB. Okay, so if it's in state QCA, if it's QCA, that means that you saw an A, right? If it encounters an A here, so you go to QCA. If you encounter a B, then you go to QCB. Okay? If it's a B, you go to QCB. Now, again, the state names here represent something. So, at QCA, that means that you're looking for C. Okay, so C is what you're looking for, this one. And you are telling the Turing machine that while I'm looking for C, after you find C, you're supposed to look for A because A was what I found earlier, and that is what you should be pairing off. Okay? And then the same with QCB. So first look for state C, and then after you find state C, pair it off with a B. Okay? Does that make sense? So change to this either QCA or QCB and then go right. Once it sees A or B for QCA or QCB, it will just ignore that because that's not what it's looking for. It's looking for C, right? So once it sees the C, okay, QCA on C will change to state QA. So once it have found C, then it will just go to QA, meaning I'm now looking for A after C. Okay, and then the same for QCB, it will go to QB. I'm looking for a B after C because B was what I found earlier. Okay, and then you keep going to the right, and then if QA sees an A, you mark it as a Y. So that means that this will be changed to a Y. And again, we're using different markers here to signify the first half and the second half. And then you do the same if QB finds a B, you mark it with B and change back to QX. That means that you're supposed to go back to the left and find the X, the last X that you marked, so that you can move on to the next symbol after it. Okay, so if you encounter Y's along the way, you should ignore it. If it's in QX, if you see an A, B, C, or Y, that's perfectly fine. You should ignore it. Just keep going to the left, and once you see an X at state QX, change back to Q0, which is the start state, and then you go back to this state here. So it will just loop and loop. So this will be X again, and then this will be Y, and then it will stop if you're at state Q0 and you find C, because this is already the middle. So that means that if the string is part of the language, then you should have paired off everything already. So once you see the C, which is the middle, you're done processing the string, so you should change to state QE, which is looking for the end of the string. So at QE, you're only supposed to look at Ys, and Ys are all processed already. Okay, and just ignore them, just go to the right, and once you see the blank, then it's already the end of the string, so everything is processed, so you change to the accepting state QF. Okay, so I hope that explanation somehow made sense. If you put everything together, this is how it should look like. Okay, so I'm not going through it again. Just follow this like description, and the more formal version is this one. Okay, so let's go through the example of this one. So let's see A B C A B to see the behavior. So you're at Q0, the start state. You see an A, so you'll mark this with an X. Okay, and what state will you transition to? You'll go to QCA, right? Because you're supposed to look for C first, and you're relaying the information that, hey, I saw A. Okay, so at QCA, you're looking for C, so if it's B, ignore. Now it's C, so you go to, you've done the C part, so you just go to state QA, okay, and move to the right. At QA, you saw the A that you're looking for, so this will be changed to Y, because this is the pair of the X here, okay. So this will be changed to to Y, and then we go back to, oh sorry, let me do that again. Okay, so at QA, we found the A, so we mark this as Y, and then you will look for the QX. So we are in state QX, so we're looking for X. So go back and find the X, and then once we see the X, then we move back to the right and repeat. So we're going back to start state. Now this is a B, so we'll go to QCB, and then now we see the C, so it's going to QB. Okay, now it sees the B, so that's the pair. We mark it as Y. Go back, find the X. Now we found the X, so we go back to Q0, and now we see the C, which is already the middle, so we're done. So we should go to the end, and we should only encounter Y's. And now that's the end of the string, so it is accepted. Okay, so yeah. Now, what if it was not um, part of the language? Okay, AB is here, but on the other hand, it's BA. So what will happen? So it's looking for A, but then it saw a B, right? It should not see a B, because the first thing that should be here is either A or a processed Y. But since it saw a B, then it is rejected. Okay, how about if it's like this? Okay, okay, this time it sees the A, it's paired off, it sees the B. Okay, so it's looking for a B, but then it encounters an A, so it's also rejected. Okay, how about if it's BB, C, BB? Okay, looking for a B, go back, mark it as X, find the pair, go back, find the C, and then to the end. So that's accepted. But what if there was one more B here? Okay, and then let's speed it up. What will happen? So it will pair off the first two B's. Then once it sees the C, shoot. Let's do that again. Sorry. Once it sees the C, it should go to the end and look for the end of the string, and it should only process Y's, right? Meaning everything should have been paired off. But we encounter a B which has been not paired, So this is rejected. We'll stop because it's not defined for QE to encounter a B. Okay. Lastly, what if there were more B's here? So the first two pairs would be matched again, but then the third one would be, ouch, again. Okay, the third one is looking for a B now, but it doesn't find the B. It finds the end of the string, so this is also rejected because there is one X here that has no Y. Okay, so that is WCW. Okay, and then finally, the last Turing machine that we'll discuss is how to add 1 to a given binary number. So this time we'll use the Turing machine with infinite tape in both directions. So in our illustration, we've actually been using an infinite tape on both directions. So it should be fine. So example, if you're given 0 and then you add 1, it will become 1. If it's 1 and then you add 1, it will become 1, 0. If it's 1, 0, 1, if you add 1, this will become 1, 1, 0, right? So from your binary addition. So it's actually pretty straightforward how to do this. At the start, you go to the right until you reach the end of the string. Okay, so until $sign is found. And once you find it, go back to the left, and then this is how you will add the 1. If you see a 1, change it to 0 and continue to the left. Okay, so that means that you added 1 to it, so 1 plus 1 becomes 0, and then you carry 1, so you go to the left and add more 1s. If you see a 0, change it to 1 and stop because 0 plus 1 is already 1 and there is no carry over. Okay, so we can stop. But if you see another 1, change it to 0 and go left still, so it will continue until such time that we either see a 0 or the $sign, meaning the start of the string. Okay, if it is the start of the string, we change it to 1 and then we stop. Okay, so that is how we add 1 to the end to the binary string. So at QE, you go to the end, you ignore everything, and then you go to QA, which is the adding part. If you see the end of the string and go to the left. If you see a 1, you change it to 0 and continue to the left. If you see a 0, you go you change it to 1 and then you um, transition to the final state. So you stop and then you go to the right. And then if you also see the end of the start of the string, so because you're going to the left, you're supposed to find the start of the string, right? Um, then you change that to 1 also, and then you transition to the final state. Okay, so let's try that. If it's 0, 0, 1, what will happen? So you go to the end of the string, and then you go back to the left. Now it's a 1, so this should be changed to 0 and continue to the left, right? So it's a 0, so we'll change it to 1 and then we'll stop. That's it. So 0, 0, 1 plus 1 is 0, 1, 0, right? How about if we do 0, 1, 0? Okay. Okay, to the end of the string. And then we encounter the 1, we encounter the 0 at the end of the string. So we can immediately change it to 1 and then just stop, right? Now how about if it's 0, 1, 1? Okay, what will happen? So we're at the end of the string. 1 will be changed to 0, then go left. 1 will be changed to 0, go left. 0 will be changed to 1, and then we'll stop. So that's it. So 0, 1, 1 plus 1 is 1, 0, 0. Now what if it's 1, 1, 1? Load. Go to the end of the string, go back to the left, 0, 0, 0, and then the blank will be turned into 1, and then we stop. So from 1, 1, 1, it became 1, 0, 0, 0 when we added a 1 to it. Okay, so pretty straightforward, right? So that's it. Okay, So for Turing machine languages, we can actually define it in two ways. Okay, so either by final state or by halting. So Turing machine by final state is defined as follows. So the language of the machine is all strings W such that if you start at the this ID, so starting at the start state with the input string in the tape, it eventually goes to an ID with an F, meaning it has a final state. Some instantaneous description where the state is a final state. Okay, so eventually it reaches a final state. So yeah, accept the string if the Turing machine reaches a final state. And then for by halting, h of m, the language of the Turing machine by halting, is defined as a set of strings w such that starting at the starting ID q sub 0 w, it eventually goes to an ID h where ID h has no moves left. So it's an instantaneous description that halts or that cannot move anymore. Okay? So accept the string if the Turing machine eventually halts. And these two are actually equivalent. Okay, we can just convert TM by final state to TM by halting and vice versa. Okay, so how do we convert it? First, if it's by final state to halting, okay, so given the TM by final state, so for each final state of the given Turing machine, remove any movement so that it will stop. Okay, so the TM halts in that state. So you remove any movement from the final state. And we also need to avoid having the Turing machine accidentally halt, right? Because some entries in the transition function might not be defined. So if it's undefined, it will also stop, right? And we don't want that because if stopping in Turing machine by halting means that it's accepted. So we don't want it to accidentally halt. So what we'll do is we'll add a state S that runs to the right forever. Okay, so we'll add a state which will make it not stop. Okay, it keeps running to the right. So for each symbol x, we will add s on x. Will keep on running to the right. Okay, it will stay at s. It will keep the symbol and just go to the right. Okay, and then for each state that is not a final state, and for each symbol, if it's undefined in the transition function, then we'll add a transition to S. So S, and then keep the symbol and then go to the right, so that it will keep running to the right forever if it's undefined. Okay, so this is to avoid accidentally halting. Okay, so that is by from final state to halting. Now on the other hand, if it's from halting to final state, then we'll just add the state f, which is the only final state of the equivalent Turing machine, and then there should be no transitions for state f, so that it will yeah, no transitions for state f, so that it's already the final state. And for each state q and symbol x, if qx is not defined in the transition function, that means that you are stopping in that case, right? So if it's undefined, then you transition it to the final state so that it is accepted by final state. Okay, so yeah, all of the possible stoppage of the Turing machine, just make the transition to the final state for the equivalent TM by final state. Okay, so yeah, it's pretty simple how to convert between the two. Now, let's talk about the two different types of Turing machine. So first is the recognizer. So the recognizer is given an input string, and the recognizer will either accept the input string, reject the input string, or stay in an infinite loop. Okay, so the recognizer is not guaranteed to halt because one of the outcomes is it will keep on looping forever. Okay, so all Turing machines are recognizers. Turing machines in general are not guaranteed to halt, okay, or to stop. On the other hand, there is a special type of Turing machine called the decider. So if you give it an input string, there are only two outcomes. Either it accepts the input string or reject the input string. Okay, so it will be guaranteed to halt on all inputs. That is why it's called a decider, because it can actually decide. Okay, it may take a long time, but it is guaranteed to halt eventually. Okay. However, in general, not all Turing machines are deciders. All Turing machines are recognizers, but not all Turing machines are deciders. So not all Turing machines are guaranteed to halt on all inputs. Okay, they may halt or they may stop on some inputs. They may stop on most inputs. But if we are talking about guaranteeing it for all inputs, that's not true for all Turing machines. Okay, so yeah. So for Turing machines and their equivalent languages, we have the following. So a language L is Turing recognizable or recursively enumerable if it has a recognizer Turing machine. So pretty straightforward, right? Turing recognizable if it's a recognizer Turing machine. And remember, recognizer is not guaranteed to halt. Whereas if it has a Turing machine decider, which is guaranteed to halt, then that language is Turing decidable or recursive. Okay, so in this course, we will use the recursively enumerable and recursive languages na um, labels. Okay, so we have the following. So Turing decidable is recursive, Turing recognizable is recursively enumerable, and you'll notice that recursive languages are inside recursively enumerable because recursive languages are also recursively enumerable, right? But not all recursively enumerable are recursive. Okay, so if it's decidable, it's also recognizable because this is a smaller language class, right? This one is the bigger language class. So a recursive language is also recursively enumerable, but not necessarily the other way around. So for recursively enumerable languages, a language is recursively enumerable if some Turing machine recognizes it. So there's a recognizer Turing machine. So if the input string is part of the language, then the Turing machine will enter the final state or will halt. But if it's not part of the language, it will either enter a rejecting state or it will loop forever. So it's not guaranteed to halt. Okay. So in the case that it's not um, if it's taking a long time, it might not be clear whether the Turing machine is taking a long time because it's still doing its computation and it might eventually lead to a final state later on if you just waited a few more minutes. Or is it because it's taking a long time because it's really stuck on a loop, and even if you wait how many years, it will not stop because it's not part of the language, right? So there's that dilemma, right? So we don't know whether taking a long time is because the Turing machine is still computing or it's already stuck on a loop. Okay. For recursive languages, it's more straightforward. Okay. So a language is recursive if some Turing machine decides it. So it's a decider Turing machine. So if the string is part of the language, then it will enter the final state. If it's not part of the language, then the Turing machine will enter the reject state. And in both cases, the Turing machine is guaranteed to halt. Okay, so just wait for it to stop and eventually it will be decided whether it's accepted or rejected. Okay, so we have now seen uh, many different types of language classes. So we are now ready to discuss the Chomsky hierarchy of languages. So the Chomsky hierarchy of languages was described by Noam Chomsky in 1956, and it's the hierarchy of languages. So from the smallest level, which is the regular languages, it has the computation model of finite automata, right? So we've seen this. Then the context-free languages, you have the non-deterministic push-down automata. After that, you have context-sensitive. So if it's not context-free, it's the next one is context-sensitive. So it uses context. And this one is modeled by linear bounded automata. So we did not discuss this, but there exists a language class called context-sensitive languages. And then finally, the most general of all is recursively enumerable languages, which uses unrestricted grammars, and the computation model is the Turing machines. Okay, so okay, so we have here the illustration for the Chomsky hierarchy. So at the very bottom, or the smallest language class, is the regular languages, and then on top of that is context-free languages. Then on top of that is context-sensitive languages, and then on top of that is recursively enumerable languages. And then outside of that, there are languages that are not recursively enumerable. Okay, so they can't be modeled with a Turing machine. Okay, so its corresponding automaton or automata would be the finite automata, smallest. On top of that is the push-down automata. And then on top of that is the linear bounded automata. And then Turing machines has the most computing power. Okay, so that is the hierarchy of languages. So if we also talked about recursive languages, right? So where does that fit in the hierarchy? So it's actually in between context sensitive and recursively enumerable, because some recursively enumerable languages are just recursive languages in that they have a decider. Okay, so it's guaranteed to stop. Okay, so that is also more powerful than context sensitive languages. Okay, so that is the full hierarchy. So um, under this hierarchy, we have different grammar types. So we have the regular grammar, or the for the regular languages, context-free grammar for context-free languages. You have the context-sensitive grammar and unrestricted grammar. Okay, so we've seen the first two types, but we haven't seen these two yet, right? So we'll look at them briefly today. So for regular grammar, of course, you have the three operations for regular expressions. You have the union, so you have the A or B, and then concatenation, A, B, and then closure, so AS or epsilon, wherein you can repeat S as many times as you want, right? So union, concatenation, and closure are the three operations for your regular expressions. So this is how the regular grammar looks like. For context-free grammars, we've also seen this. So it's in the form A, it's a variable. The productions are of the form A is to beta, wherein beta is a mix of variables and terminals, or it could also be epsilon. But the left-hand side is always just one variable. Okay? And then this one could just be a mixture of variables, terminals, or also epsilon. Okay. Now, how about for unrestricted grammar? For unrestricted grammar, this is the grammar for recursively enumerable languages. Okay, so the equivalent for Turing machines. So this time, the productions are of the form alpha is to beta, wherein both alpha and beta is a mixture of variables and terminals. So whereas in CFGs, you only had a variable in the left-hand side, here in unrestricted grammar, you could have a mix of variables and terminals here as well. Okay? For as long as the left-hand side is not epsilon. Okay. This one could be epsilon, but not the left-hand side. Okay, so that's the only restriction. Okay, so an example of an unrestricted grammar would look like this. So this is for the language A 2 raised to n. So it's an exponential number of a's. So 2 raised to n. So if n is 1, so that's a raised to 2. If n is 2, that would be a raised to 4. So 4 a's basically. So this is the unrestricted grammar that represents this language. We won't discuss as to how or why that is the grammar itself, but just know that this is how it looks like. Okay, so you'll notice that in the left hand side, there could be single variables, or it could be a combination of variables and terminals, like so. Okay, so let's try to derive um, the string AA from this grammar. So let's derive AA. So from S, we have LAR. You have this one, right? And then this L could be replaced with this LD, right? So this becomes LDAR. And then this L could be replaced with this epsilon. So this will become epsilon DAR. Okay? And then this DA here could be replaced with AAD. So since this is epsilon, we can just ignore that. So this DA could become AAD, and then we follow it with the R. Okay? Now, this DR, we don't want this anymore because this is what we want, right? So we can replace this with an R. So AA with an R, and the R will be replaced with an epsilon eventually. AA epsilon, so it now becomes AA. So S has now derived AA, which is what we wanted in the first place. Okay, so it's kind of weird, right? Because you could have, we're not. It's not weird. We're just not used to it yet, right? So we could look at either um, one variable, or a pair of a variable and a terminal, or a pair of a variable and a variable together, and replace it with another variable, or a mixture of variables and terminals. But yeah, that's the power of unrestricted grammars. It's that it doesn't have restrictions on the left hand side anymore. It could be a mix of variables and terminals already. Okay, so yeah, so that was the um, derivation that I showed earlier. Next, we also have the context sensitive grammar. The context sensitive grammar is an unrestricted grammar with no length decreasing production. What does this mean? So it also follows the alpha is to beta pattern. Okay, so this could also be a mix of variables and terminals. This is a mix of variables and terminals. However, there is a restriction on the length, in that the length of B here should always be greater than or equal to the length of A. So this one should not be shorter than this one. So if there are two here, if there are two variables and terminals here, it can't just be one here. It should be two or more. Okay? So yeah. So the equivalent automata for this one is called a linear bounded automata, which is somehow similar to a non-deterministic Turing machine. But we won't get into that. Just mention it briefly here. So let's see an example of a context-sensitive grammar. So this one is for AN, BN, CN. And if you recall from our context-free languages and push-down automata and the pumping lemma, we know that this is not context-free because it counts three things, right? The number of A's, the number of B's, and the number of C's. But this one is context-sensitive. So this has the corresponding grammar given here. And you'll notice that, for example, this one is length 1. So the right hand side is length 4, length 3. So it always has more or equal to the length of the left hand side. So this one is 2. So this one has 2. 2 here, 2 here. And then the rest also has length 2, length 2. So it does not decrease the length of the left hand side. Okay? So let's now try to derive the string AABBCC. Okay? So let's try that. So we're going for AABBCC. So let's start at variable S. So we can replace it with ASBC. Okay. And then what we'll do is this S could be replaced with this ABC here. Okay. So this would be A. The S would be replaced with ABC. And then we'll just copy the BC here. Now, eventually we want to reach the BBCC, but currently we have the BCBC. Fortunately, we have this production. From CB, we could flip it to BC. So this CB, we want this to be BC. So this will become AA B, and then this will become BC, C. Okay, so from CB it became BC. Okay, now it kind of follows the form that we're looking for. And then from here, we have AB here will be transformed to AB, wherein the B is already a terminal. So this AB will become AAB, BCC. So we have three variables still, but then BB will become BB. So that will become BB. So that became this. And then there's still the variables CC. And then this BC will become BC with a terminal. So that's BBC with a capital C variable. And then finally, the CC variable will become CC with a terminal. So we have now derived AABBCC. Okay, so that is an example of a context-sensitive grammar. Okay, so it's also unrestricted, but it's uh, the length does not decrease from the left hand side to the right hand side. Okay, so yeah, that's it. So to review for the grammar types, you have the regular languages, you have the union, concatenation, and closure. For context free, you follow A is to beta, where A is a variable and beta is a mix of variables and terminals, or could also be epsilon. For context sensitive, it's alpha to beta, where alpha and beta are both mixtures of variables and terminals, as long as alpha is not an epsilon. And the length of beta is greater than or equal to length of A. So it does not decrease the length of the left-hand side. The length of the left-hand side, yeah. And then for unrestricted, then it's just alpha is to beta, where it's a mix of variables and terminals. Okay, so that's it. And then again, this is the hierarchy of languages, right? From regular to context-free, to context-sensitive, to recursively enumerable. Okay, so that's it for this video. So to review, we have discussed the Turing machines, its 7-tuple notation, how to write its instantaneous descriptions. We saw 5 examples of how to design Turing machines. So you can practice designing them through the assignment that we have. You can also study the examples given so that you can have an idea of how to design Turing machines. We also discussed the difference between Turing machine by final state and by halting, the recognizer versus the decider Turing machines, the difference between the recursively enumerable and recursive languages, and we also saw the Chomsky hierarchy of languages. Okay, so that's it for this lecture. In the next video, we will be talking about extensions to the Turing machines. So how do you program a Turing machine? So what are the programming tricks that we need to use to be able to implement the Turing machine? Um, we'll also see some Turing machines with restrictions and extensions, meaning more capabilities. And then we'll also discuss the closure properties of recursively enumerable and recursive languages. Okay, so that is in the next video. So if, by the way, the demos that I showed you earlier can be found, or you can do that in turingmachinesimulator.com. The actual code for the Turing machines are included in the assignment that is for the Turing machine. So you can find that in the zip file. But you can go to turingmachinesimulator.com to run those examples. Okay, so if you have any questions, don't hesitate to ask me, and I will see you in the next video.